Welcome to Module 28 of Engineering Vibrations 1, an Introduction to Single Degree of Freedom Systems. Today's learning outcome is to solve for the differential equation of motion for a rotational system undergoing free damped vibration. Here's our system. This could be a model of some sort of suspension system. We've got a bar here, and then we've got a damper and a spring acting upon that. And we have measured, we've taken some real-world suspension system, and we've measured the decaying oscillations. And we have a measurement for theta 1, the angle that the suspension system goes through for the first peak, and then the 10th peak. And I've placed those on my graph. So we're going to determine in a series of modules here the differential equation of motion of this system, and then the natural frequency and damping factor, and how long it took to decay from, how long it would take to decay from 0.1 radians to 0.02 radians. Okay, so here we go. The first question I have is, for part A, we want to find the differential equation of motion. And so what should we do first? And this should be pretty familiar to you by this time. So stop the video and talk about what you should do first, and when you have your answer, come on back. And so you want to draw your free body diagram equals kinetic diagram. I'd ask you to go ahead and do that, and again, once you have that done, come on back and see how you did. Okay, so there's the system. I want to draw the free body diagram equals kinetic diagram in the displaced position. Even though I'm showing rather large displacements, angular displacements in my diagram, it's not to scale. We're assuming small displacements. And so I have my pin reactions at the left, my damper force, which is C times the velocity at the damper, times K, or with a K force at B sine of theta for the displacement at the spring. And then on the kinetic diagram, I've put my three vectors at the mass center. I have my mass times acceleration and tangential, which ends up being mL/2 theta double dot, which we saw earlier in the course, and our mass times the normal or radial acceleration, which is mL/2 theta dot squared, the angular velocity squared, which again we saw in the earlier in the course. And then for this bar, the mass center has a velocity, a tangential velocity and acceleration, but it also has an angular acceleration because it's rotating. And so I have some I about the mass center, G, times the angular acceleration, theta double dot. So that's a good free body diagram equals kinetic diagram. Once I have that, I want to sum, I'm going to sum moments about R, because I'm really not interested in the force reactions at R, and come up with an equation of motion. And so I've got C times the angular, or the term here for the velocity, and then I have to multiply that force times its moment arm, which ends up being A cosine of theta. Then I have K B sine theta, which is the force in the spring, times its moment arm, which ends up being B cosine theta. And on the left or right-hand side, that equals my mass times L/2 theta double dot, which is the mass times acceleration. It has to be multiplied by its moment arm to become a moment. And then I have the IG theta double dot, which is already a moment. Both of those are clockwise. My sign convention was counterclockwise positive, so they become negative. Now, since we're doing small angles, cosine theta becomes 1, sine theta becomes theta, and we get the equation to become linear at that point. I can also look up, or you should become familiar by now, that I sub g, the mass moment of inertia for the slender bar about its mass center, is 1/12 ml squared. And then collecting terms, I get mL/2 squared, which is L squared over 4, L squared over 4 plus 1/12 ml squared theta double dot is equal to 3 L squared over 12. And so I have 4/12 ml squared theta double dot. And that's equal to 1/3 ml squared theta double dot. And then I have my damping term and my spring term. And actually, this should be a plus, right? Because I've got plus, plus, and minus. So when I take those minuses on the other side, all of that equals 0. And so that's my DEOM. Here I've multiplied by 3 and divided by ml squared. So I've got the coefficient of my acceleration term equal to 1, which is the standard form. And so that's it for this module, where we solved for the differential equation of motion for that suspension type system undergoing rotational motion and free damped vibration. And we'll come back next and continue on with this problem.